you're watching from. This your favorite tutor me or Morewa. Today has been quite amazing. This happened to be the third subject that I'm taking today. Earlier today, that was in the morning, I taught physics, and then I was actually teaching half-life and decay equation, and I saw several questions on my Facebook Live or more. Check it up. If you're watching me any part of the world, Yomi Omorewa is the name. You check it on Facebook, you'll see the teaching on half-life and decay equation, and you will see the various formula that I came with and how I dealt with those various questions. And then in the afternoon, I continue with my calculus class, which I started about 2 days ago. Today, I was able to cover differentiation of product rule and differentiation of quotient rule. And then I went on YouTube Live to teach chain rule and also implicit function. And to conclude today, I want to take chemistry. As a science tutor, I take math, I take physics, and I take chemistry. And tonight, I'm looking at this interesting topic, and the topic is hybridization and shapes of molecule. Hybridization and shapes of molecule. This is an interesting topic for undergraduate students, and of course for some of our students in the secondary school or in colleges. Okay, look at this topic very well. Hybridization. Hybridization actually is a blending, or what you call the mixing of two pure atomic orbitals to form a new hybrid. With the same energy level. This is so interesting and very important. Hybridization is the blending or the mixing of two pure atomic orbitals to form a new hybrid with the same energy level. The underlined words are very important. Two pure atomic orbitals and then forming a new hybrid and of the same energy level. So this is so important. It means that you cannot really mix 1s orbital to 2p orbital. That won't work. Neither can you mix 2x orbital with 3p orbital. That won't also work. So it must be of the same energy level. That's very important for you to note. Okay, now we have, from what I've said now, you know that if we talk about hybridization of sp3, we talked about hybridization of sp2 and hybridization of xp, hybridization of sp3d. What this thing means is that you have 1x, you have 3p. That's what it means. So it means that your x here is contributing 25%, and then your p here is contributing 75%. And then when you come here, it means x plus p plus p. What that means is that if this is 33% in the x orbital, it means that this is what? 67 what percent. That's what it means for the p orbital. Okay, then when you come to x now, it means that x plus p, and this is like 50% is being contributed, and then for the p orbital, 50% is also being contributed. I hope that's very clear. Actually, I've not started. I'm just trying to explain the XP3 hybridization, the XP2 hybridization, and the XP hybridization. Okay, so I like to start with carbon. So let's look at carbon. Let's look at carbon. Carbon has electronic configuration of 1x2, 2x2, and 2p2. That's the electronic configuration of carbon in the ground states. In the what? The ground states. That is uncombined states. And then what happened as we put it in the let me put it well. So we have oh no, what's this? I'm trying to give a space. Okay, this is better. Yes. Okay. I want to explain this now. 1x, 2x. Why p orbital has three degenerate orbital. Let me explain that before I start. Not many students will understand what I just did now. So it's important I explain that. Actually, we have our XPDF, and in your basic school, you were told that this is spherical in shape. That the x orbital is spherical and it has no degeneracy, or it has no degenerate number. Okay, P is dumbbell, that's the name, and it has three degenerate orbital: 2px, 2py, 2pz. I'm going to draw it. And then D has five degenerate orbital, and it is called double dumbbell. And F is called complex. F is called complex. Okay, so X is spherical, something like this. X is spherical, that's for X orbital. And then for P orbital, you have something like this. For the X part, yes, that's it. That's it. And then we have for Y, that's for Y. Now, I guess you are following now. Then how about the Z? How about the Z? The Z now is this way. So this is Z, 2PZ. This is 2PY. And this is 2PX. Are you following? And so this is it. This shows that the p orbital has three degenerate orbitals, which x orbital does not have. And this is why we have now. So what's the maximum electron for x orbital? It is 2. So we have 2. Let me put it this way. What's the maximum electron here? 6. What's the maximum electron here? 10. And here, of course, is 14. Okay. Now, if I'm going to fill this place up, so I'm going to have from electronic configuration now. So I will have here 2, and then 1. So electron must go in singly first. Electron must go in singly. It will be wrong to put this here. No, do not do that. It will be wrong to do so. So it must go in singly according to Ohm's rule. If you put the 2 here without putting here, you have violated Ohm's rule of multiplicity. So electron goes in singly before pairing will occur. Okay, so what we have here is 1, 1. Now you will discover that our 2pz is not being touched, nothing happens to it. So this is what happened at the ground state. At the excited state, what happened? You may want to know what we mean by excited state. At the ground state, I asked a question from someone who was teaching, and then I needed to find out that does carbon form its bonds in the ground state or in the excited state? You may want to ask too, does carbon form its bond in the ground state or excited state? Obviously, it does not form its bond in the ground state. The reason is because at the ground state, only 2 electrons are available. Only two electrons are available. Okay, and that cannot form bonds. We need 4, minimum of 4. Okay, for it to undergo its covalent bonding. And so at the excited state, the 4 electrons are available, hence carbon form its bond in the excited state, not in the ground state. Okay, so at the excited state, what happened? So let's see, this is what happened at the excited state. Please, I'd like you to really follow, really follow. So please, you can share on the other. So you have 1x, 2x, 2px, 2py, and 2pz. So here you have 1x, 1. Remember, this is 1a. It's not even compatible. So we're going to scrap this. It's not part of the show because we don't have 1p. Remember the definition of hybridization, that it is a blending or mixing of 2 pure atomic orbitals to form a new hybrid with the same energy level. And so if it is the same energy level, we do not have anything like 1p anywhere. So the 1x is just there as figurehead. It will not be employed in our bonding or hybridization. And so we have 2x here. It was 2 here. What will happen is that the other one here will jump. Remember, this one has been there before. So this empty space, what is here, will jump to this place. It will jump there. This is what happened. And so you have 1x here and you have 3p here. And then that gives you 3p this. This is what we call the single bond. So all single bond like methane, ethane, propane, butane, alkane generally, they fall under this category, tetrahedral. Okay, so you have xp3. Methane, for example, is tetrahedral. So you have this now for methane. And then the alkane members have sp3. And I hope you know why it is sp3. It is because it is all sigma bond, no pi bond. Hey, I'm saying another thing again. There is no pi bond here, all sigma bond and no pi bond. The question someone may want to ask, excuse me, sir, what is pi bond and sigma bond? That takes me quickly to this. Let me explain this quickly. Sigma and pi bond. Pi bond. Remember, I said that the hybridization here now is sp3. So The X is 25 and the P is 75. So that's what you have there. Okay. Uh, all sigma and no pi bonds. Okay. Now, if we want to do this is for alkane. This is for alkane. Now, if I want to do for alkane, I'm coming back to explain pi and sigma bond. I'm coming to this. I'm coming. Let me quickly explain something here. I'm coming back to explain pi and sigma bond. So let me finish off something here. If I want to explain that of alkane, in other words, the XP2 hybridization. If I want to explain the XP2 hybridization, what will happen is that it's still the same thing. I don't want to rewrite again. The ground state of carbon is already stated here. So you have the 6, 2, 2, 2, that's 6. And then you have the 6 here at the ground state. At the excited state, what happened? The same thing is going to happen. The 2x, the one that is there, will jump to the last place. But what will happen is that the 2pz in alkane, will become unhybridized. The 2pz will be unhybridized. That is the pi bond. That is the weak bond that is not hybridized. And hence we have, I'm done with alkane now. So I'm doing alkane. Hence for alkane, we will now have XP2. And so we have XP2 here. This is called double bond. This is called double bond. Now, what happened? The pi bond was not hybridized, and that's the 2pz. I'm sure that's very clear, right? Yeah, that's very clear. Okay, so let's go to the last one. The last one is the alkyne. Alkyne, that's XP. Like you have ethyne, propyne, ethyne is C2H2. Okay. Now, to do that of XP, how do we go about it? Actually, what happened at XP is that you have both the 2pz here, the 2py rather, and the 2pz become unhybridized. The 2py and the 2pz become unhybridized, and the only thing that is being hybridized is the 2px. And so you have one x and you have one p, and that becomes x what? P. And with that is triple bond. That is triple bond. Let me say this quickly again. Alkane, XP3, alkane, XP2, alkyne, XP. The first member of this is known as methane. The first member of this is known as ethane. The first member of this is known as ethyne. Let's see. Methane. Methane is C. What's the property here? Methane is one, tetrahedral in shape. It's tetrahedral. The bond angle 109.5 degree. What again do you find there? All sigma, no pi bond. All sigma, no pi bond. All sigma, no pi bond. So we don't have pi bond here. So we have 109 as a bond angle, and then the shape is tetrahedral, and then all sigma, there is no pi bond. Remember, Okay. Okay. So now you see from what I've just said now, if this is methane, now as I want to end this part of the note, and I'm coming back in my second video, I'm going to continue from here. But please take note of something. We have sigma and the pi bond, and I was trying to explain why one is greater than the other. Now look at 18. 18 is like this. 18 is like this. This first one that you are seeing here is the pi bond. The pi bond. The down one here is the sigma bond for double bond. But look at triple bond now. Look at triple bond. For triple bond, this is pi bond. This is pi bond rather. This is pi bond. And the last one is the sigma bond. In other words, for a triple bond, there are two pi bonds. For a double bond, there is only one pi bond. So this what makes triple bond to be stronger than what? The double bond, because there are two pi bonds, and pi bonds are responsible for the reactivity of the unsaturated hydrocarbon. Okay, so you might now want to know what are pi bonds and why is sigma bond stronger than pi bond. Please listen to this very carefully. Okay, now sigma bonds are formed by head-on overlapping. They are formed by head-on overlapping, and the overlapping tends to occur to a large extent. The overlapping tends to occur to a large extent. So sigma bond has strong covalent bonding, which are formed by head-on overlapping, which tend to occur to a large extent. Why pi bonds are weak covalent bonding? They are weak covalent bonding, which are formed by what we call lateral overlapping. Lateral overlapping. You can see now. Oh, this is so interesting. Okay, so this is formed by head-on overlapping, and this one is formed by lateral overlapping. How then is this one stronger than this? Well, it is stronger than this. Sigma bond is stronger than pi bond because the overlapping here, because the strength is dependent on the overlapping. Okay, the overlapping here is to a large extent, while the overlapping here is a short extent. And so this is stable and this is unstable. So this brings us to the end of the class. Thank you. Watch out for the continuation of the class.